Part C.4, linear recurrence relations. This part, we need to use math calculation to derive Fibonacci formula. So we do not assume anything. We just use the standard way to derive math formula. The technique, the method used for this part, I think you already learned in discrete math. So the method is from the discrete math. Yeah. But here, I like to go through the whole method another time because this method, I feel many of you may not be familiar with. Although you can go back to check the discrete math method to solve this problem. Yeah. But here, I also, when I go through, I also want to look at from the problem solving point of view. Yeah. So we can learn some techniques in problem solving. Yeah. All right, so let's start. First, we want to know what type of problem it is. Okay. It is a second-order linear homogeneous recurrence relation with constant coefficients. Yeah. So what's that? Yeah. Look at this formula. Second order. Here. Why second order? So look at the lowest subscript. So you start from the lowest subscript. You increase it by 1 plus 1 plus 2. Okay? So the highest one, second order. So first, second order, linear. So it is linear. So there is no square, right? There is no square, cube, you know. So all the unknown sequence number, the exponent is 1. So that's why it is linear. Okay? Homogeneous. Why homogeneous? Because there is no constant term. If you have a constant term C, it is not homogeneous. Okay? If the constant term C equals 0, then we call it homogeneous. Usually the homogeneous equations are usually easier to solve. Yeah, it is much easier to solve the homogeneous type. Yeah, with constant coefficient. Yeah, coefficient A, B constant, and B not equal to 0. Yeah. Otherwise, think about what if E equals 0. What would happen? It won't be second order. It will be the first order. Then it's too easy. Yeah, it's too easy. Yeah. All right. Now, let us solve this problem. Okay. All right. For the Fibonacci problem, it is just a special case. A and B both equal to 1. Yeah. So we simplify, the equation is like this. Very simple. Yeah. Now, let's try to solve it. Yeah. All right. Our original equation is given like this. The problem is, how do we get started to solve this problem? How do we get started? All right, yeah. So let's take a special view. We consider a sequence. This A sub k, this is a sequence. Now we need to find a math formula to generate this whole sequence. Yeah. So that's the problem. Yeah. So now the question is, in the first step, can we get the structure of the sequence? The structure. We want to guess first. So this step is very important. The guess. But when you guess, you need to base on something. Usually based on something. Here we guess the structure is like this. The question, how do you guess the structure like this, right? Yeah, that is a good question. How do you know the structure is like this? T to the kth power for some parameter t. The t should be determined. Okay? And we know if the sequence is like this, we call it geometric sequence. Okay? Yeah. All right. But here, this step is critical because if you can guess this structure, you're almost halfway in your solution. Yeah, so this step is so important. Halfway in your solution. The remaining, you just work on it and find a solution. Yeah. So that makes this step extremely important. How do you get to this point? So here, because we don't know who discovered this method the first time, right? We don't know that. Yeah. When we learn this method, someone did it. We just learned. Yeah. But here, I may try to recover what is that initial step to get to the structure. Yeah. Here, I may like to do it in this way. So let us consider first order recurrence relation, linear recurrence relation, first order. Okay? For the first order, you do, because when you do this another time, you get a squared times ak minus 2, right? You can go all the way down, so you can have ak equals a to the kth power, right? Yeah. So that's the first order. So you can see, to solve the first order solution, this is a geometric sequence, right? Yeah. The solution, the structure of the first order recurrence relation is this geometric sequence. Yeah. At least it tells us the geometric sequence is pretty close to the solution of recurrence, linear recurrence relation. Yeah, from the first order, we can see that. The second order, is that true? We don't know. We can try it. Right? All right, so that's the reason from the first order experience. Then we try to apply that experience to the second order and see if it is true or not. So that sounds reasonable. Yeah. All right, so let's continue. But when we do this, we ignore the initial condition. Yeah. Because at this point, we want to fix the basic structure. Initial condition, so that's the minor part. We will do final adjustment to fix it. Yeah. All right. Now let's work on the major part, the structure part. Then we want to find that t. Okay? In order to get a structure, we want to find that t. Yeah. Let us solve this equation. After simplification, we're familiar with this equation, quadratic equation. Okay? Because related to the golden ratio, right? To get a golden ratio, we use the same equation. By the quadratic formula, we have two solutions, 1 plus 1 minus version. Yeah. But when we derive that golden ratio number, we drop the negative solution, right? Here, we have that negative solution. But the question is, should we drop the negative solution here? The answer is no. We have no reason to drop the negative solution. No reason. Yeah. Why you want to drop the negative solution? You should have some reason here. When we do it on golden ratio, we have the reason. Because the ratio A over B should be positive. That's the reason we drop the negative solution. Here we don't have that A over B. Okay? Because our T is not based on the ratio of two line segments. It's not. Here, the T is used to give us the structure of the recurrence relation. It is allowed to use negative number. So that's why we should take it. All right, so let's move to the next step. Next step. Now, we want to apply these two solutions. Because these two solutions can give us the geometric sequences that satisfy the original recurrence relation. So we want to put it back, plug in back to our recurrence equation. Yeah. So we do it. When we plug in the first solution, we get this equality. It is true, no problem. Yeah. When we plug in the second solution into our recurrence relation, it is also true, no problem. Yeah. Okay. All right. Now, next step, critical step. Okay. All right. Definitely, we cannot assume any of these two can give us solution, right? Because we know each number, each T here is not an integer. This T not an integer, right? This also not an integer. Fibonacci number is an integer solution. So definitely, we cannot say any of these two solutions can give us real Fibonacci solution. No, it's not. Okay? And definitely we know they do not satisfy the initial condition. Right? Yeah. So next, what do we need to do next? We need to get a new solution, different from these two new solution. First, the new solution should take integer values. The sequence, integer values, all integer values. Second, satisfy the initial condition. That's the next step we need to do. All right. But we already have these two special solutions. We should not throw them into the garbage, right? So they're not garbage. They're still useful. Yeah. So the question is, how do we use these two solutions to create a new solution that satisfies the desired conditions? The two conditions I described it a moment ago. Yeah. How to do that? Yeah. All right. Yeah. So think about, is there a special way to combine two solutions? We already have two solutions. Can we use a special way to combine these two solutions to give us a new solution? That's the idea. Okay. So let's do it next. Yeah. All right. To do that, now we need to use a special concept in math. Special concept. Yeah. Here, your math background, your theoretical math background is important. When we need to combine two special solutions, there is one special commonly used way in math. You need to know it. It is very simple and very useful. Here, let me introduce that concept first. The concept is linear combination of two variables, x and y. Suppose you have two variables, x and y. Now there is a concept. It is called linear combination of these two variables. So you get a new expression, but that is a linear combination of these two variables. We use that concept. All right. The meaning is this. ax plus by. You select two constants, two unknown constants. We can determine these two constants later. But first, let us just use these two constants. A times x plus b times y, and adding together, and it is called the linear combination of two variables. That's simple. That's simple. All right. But how useful is it? How useful is it? You will see it is very useful. The simple concept is very useful. Yeah, let's see it. Yeah. Question: how to take advantage of this linearity property? Because this linear combination has that linearity property. Linear property. Okay? Yeah. So you multiply something, you add, you do linear operation on it. They preserve that linear operation thing. Yeah. So that property is very nice. Linearity property. Yeah. All right. So here, what's the linearity property? We go back to the recurrence relation. Yeah. Here we have this observation. Any linear combination of two solutions is also a solution. That's the property derived from that linearity property. Okay? Any linear combination of two solutions, because our original recurrence solution is a linear equation. So our linear combination preserves that property. Our linear combination can fit into that structure well. That's the reason we use that linear combination. Okay? All right. Now, we consider the new form, linear combination of our two special solutions. This is linear combination of our two special solutions. Now we claim this is a new solution. This is another solution. You can check. You can plug in. When you plug in, you will see it is correct. Okay? It is correct. Why? All right. Because, so let's look at here. Okay? We know this equation is correct, right? No question. Okay? The second equation also correct. No question about it, right? Yeah. Now, let's do linear operation. Okay? Linear combination operation. All right? Yeah. Multiply A both sides. Can we do that? We can, right? It's correct. Okay? A not 0, B not 0, right? Here, let's just assume non-zero. Okay? B. Okay? B. Also correct, right? Now, let's add up both sides of the two equalities. Okay? So then, after you add them up, you will see this is a new solution. This observation is critical. Okay. All right, so let's move to the next step. We know for any A and B, we hope at least one of the two non-zero. Actually, we expect both non-zero. Why? Because if one of them is zero, it cannot be an integer, right? Integer solution. We want to have an integer solution. So both of these two constants cannot be zero. That's our expectation. But how to determine these two constants, A and B? How to determine, right? That's easy because we haven't used another condition. Initial values. We have two initial values. We haven't used them. Now we will use those two initial values to fix these two constants, A and B. So our next step, we will determine A and B and solve the problem. All right, so now the last step of this problem. Okay, so our goal, we need to determine the coefficients A and B such that initial condition is satisfied. Because the recurrence relation already satisfied. Okay, so we don't worry about that recurrence relation part. The only thing that is missing, initial condition. So let's fix it. Okay, all right. To do that, let us plug in n values 0 and 1, two initial conditions, 1, 0, 1, 1. 0, so after we plug in, after we simplify it, A plus B equals 0. Okay, so you can see this equation is very simple. The sum of two constants, A and B, equals 0. Okay, and we can write B equals negative A. That means we only need to find the A value. If you know the A value, you also know the B value automatically. Okay? The second equation, we will find the A value. When n equals 1, so let's plug in A1, and we know the A1 value. It is 1. Okay? All right, so now we know B is negative A, right? We can replace B by negative A. After that, you can factor out the common factor A out, and inside sum of these two numbers, sorry. A1, Oh, what's wrong with it? Oh, it's okay. I got confused. Do you know why? The problem is, remember, B equals negative A, right? So when you plug in, replace, you have a negative sign here. Okay? So this time, you need to use the first number minus second number. After minus second number, 1 cross out. Negative 5 root 5 becomes root 5. So that's why you have 2 root 5. You cancel out 2, so you have root 5. Yes. Now it is enough to get A value. A equals 1 over root 5. And B equals negative 1 over root 5. Okay. All right. So now you can see we are ready to go back to the original form. So that's our final solution. So we are ready to go there. So when we do that, we know the first parenthesis, golden ratio. the second parenthesis related to golden ratio. Okay? But it is a negative reciprocal of the golden ratio. Okay? So when we factor in both simplification, right? So we get a final expression that is exactly the formula of the Fibonacci numbers. Here, there is no guess, right? No guess. Excuse me. Although, at the beginning, when we try to figure out the structure of the recurrence, sequence, right? The sequence that fit recurrence relation, we made some guess, right? Yeah. At that step, definitely we need to make some guess. Yeah. But we do not make the guess on the whole formula. Yeah. We couldn't. Yeah. We couldn't. Yeah. But finally, so we derive this solution. All right, so we complete this part C. Yeah. Next, we will start new topic. All right.